he's here in spirit as we want to look at his solution. To question 4. So this is the question we were working on last week. So shall we look through the solutions to that and then move on to the next one?
Yeah. Because I've got stuff.
I gather this was a less preferred question amongst everybody, was it?
I would choose it. It was fine up until like part 4 or 6.
Yes, same.
Yeah, it got a little bit challenging then.
Yeah,
But
that's where I stopped.
I hope we actually see the solution that, doable, Okay, so definition of normal subgroup. Okay, so what do you want? So this is the kind of initial direct definition. It's normal if any G and G, left coset represented by G is equal to the right coset represented by G. Yeah. You could have had another, so he'd scribbled out, when he'd scribbled out there was one of the alternative equivalent conditions. Conjugate of H by the element G is contained in H. It's actually going to be equal to H, but contained in H is all you have to prove. So that's fair enough. Part B, yeah, so there was some discussion about this. Show that the alternating group A4 is normal in the symmetric group. So here the argument is on making use of the general fact that anytime you have a subgroup which is got index 2, meaning it's exactly half of the group, half the size of the group, then it's automatically normal. Okay? So that's the argument he's given here. So as the order of A4 is half of the order of S4, okay, we can take that back. A4 is exactly 2 left cosets in S4. A4 and okay, so you're taking an element, a single transposition, which is not in A4. Yeah, so it's not, that's an odd permutation, so it's one transposition. So the coset represented by it will not be different from A4. It has to be something completely disjoint from A4 then. It has to have the same size as A4. But if A4 is already half of the elements from S4, the only option then is to be the complement. Okay, everything else that isn't in it is in A4. So there's just 2 left cosets. Similarly, there's 2 right cosets. A4 and its complement. So per part A, we want to show that for every little G in S4, so for every permutation G, the left coset represented by little g is equal to the right coset represented by little g. And so that breaks down into 2 cases. Either little g has come from A4 or it's come from complement. If it's come from A4, then both the left coset and the right coset are just equal to A4, he's saying. If it comes from out of A4, then both the left coset and the right coset are the only other coset that's available, which is the complement.
So that notation is, I don't remember that notation.
Yeah, so that's set difference. A less B, or the complement of B in C. So it's the set of everything in A such that X is not an element of B. Some books would write it, some books would also write it A minus B. Yeah.
This is similar to the factor group notation.
Yeah.
It's a bit.
Oh yeah,
Yeah. I mean,
yeah. It's backslash then.
yeah.
I guess A minus B is, yeah. I mean, I don't know. And then you'd be tempted to think of, yeah, like addition of sets or multiplication of sets. I don't know. This is potentially confusing, especially when the things in A and B are numbers that might be subtracted. That, This has got nothing to do with subtraction of numbers. It's to do with subtraction of elements or removal of elements. Yeah. So that's the argument there that A4 is normal. I actually started writing down an alternative one which didn't rely on the half size fact. And there I was showing directly, in fact, I think I was proving this condition here. So I was going to say if you take any any, there's an alternative way of proving it. If you take any sigma in S4, then you want to show sigma A4, sigma inverse is a subset of A4. So you let tau be an element of A4, and sigma tau is sigma inverse. Question is, where is this? But if you think of how many transpositions this needs, well, tau, because tau is an element of A4, it's expressible as an even number of transpositions. So these are Ti are 2 cycles, transpositions. Okay, but it has an even number, so tau 1 to tau 2n. That's because it comes from A4. Sigma has some number. So this is sigma, this is tau. Sigma just has some number of 2 cycles. I don't know whether they're odd or even number, because it's just a general permutation. Well, what is sigma inverse? I can write down sigma inverse very consistently with this. How do I write down sigma inverse? Given I've written sigma as sigma 1, product of these.
Sigma n minus 1, sigma
Yeah.
n minus 1 minus 1.
Yeah. Can we improve on that notation? Any? It's correct, but we can make an improvement to clean it up a bit.
You don't need the inverses.
We don't need the inverses because these are 2 cycles, they're transpositions.
Okay.
So an inverse is, they're all self-inverse. So actually, these inverses are correct, but we can also get rid of them because each of those is self-inverse because it's a 2 cycle. But the order has changed, obviously, because we're talking about sigma inverse. And so how many 2 cycles are here? 2n plus m plus n. So it's 2 times m plus n transpositions, 2 cycles. Therefore, it's an element of it. Because it's an even number of transpositions.
Is that what in the model, you put it in the model as well?
Well, it's just there for the moment, so
What was?
Let's write it down then.
could do. I'll take a photo of it and I'll crack that on the. I'll attach a photo to the video description.
So does that prove?
So what I'm proving there is this alternative condition.
Yeah.
So this is another way of saying A4 normal. Yeah, this is one of the equivalent conditions. That when you conjugate the subgroup by any other element from the group, you remain in the subgroup.
Right, okay.
Yeah.
Yeah.
So I'm proving that. So I prove that by taking a typical element from A4 and showing that when I conjugate it, I end up in A4. So you could, well, so maybe you need another implication, therefore sigma A4, sigma inverse is contained in A4. Because all of its elements go in.
Yeah.
Go into A4, yeah. So therefore A4.
That was nice. Thank you.
Which one is nicer?
That one. Like, it's just a more practical.
It's maybe more direct, maybe. But Jan's one is good as well. Jan's method, of course, can apply in tons of other situations. Anytime you notice a subgroup which is exactly half the size of the containing group, the same argument goes. So this argument, it doesn't rely on the fact that it's permutations. Yeah, it's just any group setup where you've got a subgroup of half the size of the whole group. That argument is specific to transpositions and the concept of an even and an odd transposition. This is probably going to be not distinct. Right. So it's good to see 2 different methods as well. So any other questions or points about that? Showing that the subgroup is normal? I mean, if you were given a more, maybe slightly harder, so if you're looking at a subgroup that wasn't half the size, well, then you might have to go and start thinking about these kind of ideas. And somehow show that conjugating the subgroup, perhaps by any other element, always lands you back in the subgroup. So this is equivalent to the original definition about left coset equals right coset. Okay. Okay, and then we have the big question C, which is like a big application. It's concrete. We're talking about a particular group. We're no longer talking in generalities. Yeah, so it's absolutely concrete. And so T is a group of non-singular matrices of this pattern, 2 by 2 matrices. So in order to be non-singular, it has to have a non-zero determinant. The determinant is AC. So it doesn't explicitly say so in the question, but this is equivalent, this condition here is equivalent to a non-singular. Yeah. Okay, we don't have to prove that that's a group. We can consider that that's a group. Okay, that's good. Under multiplication. And then U is a subgroup. So it's a subset of these, the special ones where both A and C are equal to 1. Okay. But little a and little c. But no restriction on x. Okay, so x can be anything. So we got to do a number of things. Prove U is a subgroup, prove U is abelian, prove U is normal in T, prove that the factor group is abelian, and then question, is T normal in the general linear group? Because of course, this subgroup, it should be, we can notice that it's a subgroup of the general linear group 2R. Indeed, it's a strict subgroup. Yeah. This is the group of all non-singular 2 by 2 matrices under matrix multiplication. T is just a particular subset, subgroup of this. So U can be normal in T, as it is. We're asked to prove that and then to examine the factor group. But if you look at a larger containing group, containing U isn't necessarily, which is kind of the implication here, isn't necessarily normal in the bigger group. Okay? So normal isn't a property of the subgroup in isolation. It's a property of the subgroup as it sits in its containing group. Okay? So if you look at it, while it might be normal in one containing group, if you expand out that group to a bigger one still, the original subgroup might not be normal in the bigger one. Okay, because you're asking more of it. Remember, the condition for normality is left coset equals right coset. But when you enlarge the group, you bring in a whole other load of other new elements, which potentially the left cosets corresponding to those can be different to the right cosets. Okay, so the condition can break down. However, if you're looking at a subgroup inside a big group and it is normal inside the big group, it will automatically be normal inside any intermediate group. Yeah. So shrinking the group will not break normality. Shrinking the containing group will not break normality, but expanding it might break normality, as we'll see in this case. Okay, now you can also take guidance from the amount of marks available. There isn't an exact correlation between the amount of marks and the amount of time or space it takes to write down stuff, but it gives you some indication of how much time to spend or how much attention to spend. So first of all, proving it's a subgroup. So ideally here you want to reference one of the subgroup theorems for that. So he goes the most direct one. So you're going to show that the subset contains the identity, contains inverses, and it's closed under the operation. Okay, we're using the fact that T is a group. It's a group of matrix multiplication, so the identity is clearly the identity matrix, and that qualifies as an element of U for sure. Okay, because U, remember, consists of all these. So the identity matrix fits that pattern with x equals 0. The inverse, So you might do a quick calculation to work out the inverse of this matrix. A particularly nice form, the inverse is minus x here in this position. Well, if this is one of the matrices from U, then this is clearly in U as well. Okay, because there was no restriction on this upper right element, so we could take any x from line. Okay. And then you look at closure, so you take two of these types of matrices, multiply them together. Quick calculation. You again get ones here and a 0 here, so that guarantees it's going to be in G. Interestingly, it turns out you get x plus y here. Okay. So multiplying these matrices, when it comes out in the wash, it seems to be equivalent to adding the top right entries. Okay, so that's kind of interesting. So why were you wasting your time proving associativity?
Oh, well, I didn't prove it. I just
Oh, you
was
didn't
like,
prove it.
it's
Oh, you
a
mentioned
property of matrices, so it.
Oh, okay, fair enough.
But I forgot to do closure as a result, because I was like, there's 3, I've done 3.
So associativity we don't need to address because associativity is given. If we're assuming this is a subset of a group, then we already have associativity across the whole group, right? So we definitely have associativity across the subset. Okay. Associativity is a property attached to all triples of elements, A, B, C. Yeah. So if it's true across the whole group, it's definitely going to be true over a restricted domain. So there's no need to go and prove associativity again. That's why it's left out in these conditions. But you do need to prove closure.
Yeah, I think I got mixed up about which
Maybe.
one I needed to
You
do.
need to address, yeah. Okay, so that proves it's a subgroup. 2 marks going, so he hasn't, he's just clearly hit the 3 parts of it. And then he kind of just summarizes the result he's using. Contains identity, is closed, and contains inverses. So therefore it's a subgroup. Prove it's abelian. Well, abelian kind of was revealed to us here. Yeah. In general, yeah, multiplying matrices, it will make a difference when you change the order. But because multiplying them seems to correspond to just adding the top right entries, when you change the order, you're still going to have the same element in that top right. You're going to have y plus x, perhaps you'd express it as, but that's going to be the same as x plus y. So that's what he just emphasizes here. Multiplying them this way, multiplying the row into the column, you might say you get x plus y there. Multiplying them this way, multiplying the row into the column, you get x plus, in fact, that way you seem to get x plus. Yeah, I think if anything, those two should be maybe, I mean, it's all the same because it's equals all the way across. But morally, I'd say when you multiply these two matrices, you do this times this, which is y, this plus this times this, which is x. Maybe that one.
Yeah, I've got them written in there.
Yeah, I think that's maybe a more natural way. Maybe y plus x there and x plus y there. I mean, it's all correct anyway because they're all equations. But I mean, it's once you get this out, you can see that it must be a big thing because this doesn't matter which order the x and y go. Yep. So it's abelian. That's basically all you have to show. Okay. Part 3, prove that U is normal in T. Well, at the top of the thing, we went to the trouble of expressing the definition. So maybe we're going to argue of the definition of normality that we have, or perhaps adopt one of the alternative conditions. So, yeah, so he's making use of this. Okay, he states it at the bottom. So this is the condition he has in mind. He wants to show that when you take U and you conjugate it by any other element from the containing subgroup T, so you look at T subset U, T inverse, that gives you a subset which is contained in U. Okay? So that's the condition he's going to use. So what he's got here is this argument for this. Yeah. Is that clear?
So what is saying?
So this is one of the conditions that's equivalent to the definition of normality. U is normal in T if this subset relation holds for every little t. Yeah. So this is what he's going to prove. So this involves the inverses of elements from T. So that's what he examines first. He establishes this formula for the inverse. So this is a generic element from T, any A, B, C, 0. That's a generic matrix in the group T. Its inverse, well, just operate the definition of inverse. It's 1 over A, 1 over C, 0, and that's minus B over AC. Okay, minus B over AC. Okay, you could do that. I mean, the determinant is A times C, so it's 1 over the determinant times the transpose of the matrix cofactors, whatever way you think about formula for inverse. Just do it, and that's what the inverse comes out as. Okay, so that's clearly, in fact, we did that before. Did we not? No, we didn't. We did a simplified version of it when we were proving U as a subgroup, where you had 1 and 1 here. But in general, this is the formula for the inverse of knowledge. Now, if you want to show this subset inclusion, what you have to prove is you have to take a typical element from U and show that when you conjugate that element from U with T and T inverse on either side, you get another element of U. And that will show the subset relation. So that's what he wants to show. He showed for any little U and for any little T, this conjugate is always in subset U. So here's any ABCX, product AC has to be non-zero, so this is our T, and this is our U, little u, or 1x1. So you just look at the conjugate. Okay? So it's all dictated from the definition of normality or this equivalent form of normality. So that's the conjugate. You got this triple product of matrices. They're only 2 by 2 matrices. This is 0 there, so it shouldn't take too long. And you can evaluate this either way. By associativity, there's 2 ways to evaluate this. Either do multiply those 2 first and then multiply that, or multiply those 2 first and then multiply by that. He's multiplied the left 2 first. So the product is A0C, and you have AX plus B up here. Yeah, because you got AX plus B. So this is multiplying T inverse. You do the math, as they say, and you get this. And the only thing we say about this here is that it's certainly an element of U, because it's 1, 0, 1, something. So it qualifies as an element. And this argument applies no matter what little U we take, and no matter what T we take. So it's completely general. So that proves normality, doesn't it? Any other approaches or any other questions or comments? What approach did you try?
I did it wrong. I did UTU because I'm an idiot.
You conjugated T by U.
Yeah, which just doesn't tell you anything.
No.
That's what I meant
Yeah.
to do. I meant to do that, but I didn't do it wrong.
How that put the normality?
Because it is, so can you,
Yeah, I know that that final result, I mean, that one.
this one?
Yeah, one, and then that matrix, the final matrix.
Yeah, so the observation we're making at the end is that this is an element of U.
Mhm.
And what we started off with was a conjugate by any element T
Mhm.
of any element U from the subset U. So when you conjugate anything from U by anything from T, you always end up in U.
Yeah, because it says that defines the any matrix belong to you. Yeah.
Yeah. So this is like, but before the permutations, that's a criterion for A4 being normal. Okay. Well, here we're just referring for U.
Yeah.
For U being normal. So you land in U. Therefore, when you conjugate the subset, so this is the whole subset U. So when you conjugate it by T, it's just the collection of all the little t, little u, little t inverse. Well, they're all in capital U, so you're definitely a subset of U. So we've established this subset relation, so therefore U is normal. in T. So you can see here very clearly how it's with reference to T, this containing subgroup. So the later question, when we enlarge this containing subgroup, well, this element inclusion might not always be true. And indeed, it does break down, I think. Okay, so once you know it's normal, then the factor group exists. Yeah. Where you factor out the large group by this non-trivial normal subgroup, and so you get a simplified view of T. So prove that the factor group is abelian. So, a few different approaches to this. This is what the way Jan approached it. Okay, so the question is prove the factor group TU is abelian. Now, to prove the factor group TU is abelian, well, first of all, you got to get a clear view on that. Yeah. A group G is abelian means for every x and y in G, xy equals yx. Okay? That's the general definition of abelian. So if you specialize to a factor group, well, it means you take any two elements from this group and they must commute. Well, what do elements of this look like? Elements look like a T1, a left coset T1, and a left coset T2. By definition, what that product of cosets means is the coset corresponding to product element T1, T2. This is supposed to be equal to question mark. I mean, this is, if it's abelian, then this equality is going to be true. And the product the other way around, T2 capital U, T1 capital U. Now, by definition, that's equal to the coset corresponding to the product element, but when the product is done in the opposite order. Okay. So the question is whether these two are equal. Okay. So the factor group will be abelian when this is yes. Yeah.
Why did you write T1? Why didn't you write T1 and then T2? Is that how you write it?
No, because it's the same U here. But I'm talking about, see, I want to talk about any two left cosets of U within T. So I have to think about two representatives for two different left cosets.
Two different left cosets
Of U in T.
Yeah, but that's what I'm saying. So if you want to notify define two left cosets of capital U in T, you shouldn't you write like T U1 and then T little U2?
Well, no, I shouldn't be talking about little u. So I'm talking about
capital T. I meant sorry, capital T little U1 all the way around.
No, we shouldn't be doing that. Remember, capital T is the large containing group.
Okay.
The elements of the factor group are cosets of the subgroup. So the subgroup is U. The subgroup is U.
Oh, okay.
So we should be taught, like, what does a coset of that looks like? Well, it's when you take an element from T, you take the left coset.
Uh-huh.
Now I want to talk about two different left cosets, so I want to differentiate these two symbols. So I just talk T1, T2.
Thank you.
You get the idea?
Yeah.
Yeah. Okay. So this is the question. This is the goal to prove that this equation follows, and then this equation will follow. These equations are just the definition of multiplication in cosets. Okay, so Jan approaches this question nicely. So he asks himself, what is the left coset of a typical element little t. Well, a left coset is this for sure, yeah. And that merely refers to the set of all products like this, where you take this little t and you multiply it by everything from u. So everything from u is all these matrices here, where x can be any real number. Okay. So he's doing this because he knows he wants to judge this equation. He knows he wants to judge this equality. So rather than dive in straight away with doing loads of matrix multiplication everywhere, he's taken the view he wants to understand what a typical left coset looks like. Because maybe if you can gain some insight into it, then maybe this judgment will be a lot easier. That's his thinking. Okay. So what insight does he get? Well, when you multiply matrices like this, you get this matrix. A0C AX plus B. Now, what's the interesting observation here? See, we're thinking here that the little t is fixed. We're taking a particular element, little t. So interestingly, the coset corresponding to this little t consists of matrices where you have AC on the diagonal and 0 on the bottom left. So that's quite nice. All the matrices look like little t in those three positions. But in the top right position, okay, t has a number b there. But in the top right position, when you look across the coset corresponding to t, what you see is numbers of the form ax plus b. Now a and b are fixed, so they come from the entries of little t, but the x varies across every real number. So what are the possibilities for ax plus b? Well, the observation is you can get any real number out of this combination. Ax plus b can be made to equal any real number at all, as long as a is non-zero. Okay? But remember, baked into the question is this condition that a times c is non-zero. So that's equivalent to a non-zero and c non-zero. Yeah. So we definitely know that a is non-zero. It's baked into the question at the start, okay? Because these matrices have to be non-singular. So this is his interesting observation. This is like a characterization of the left coset of little t. The left coset of little t consists of all matrices from capital T, which look like the representative little t in these bottom three entries. Must have A, must have naught, must have C. They can have anything it likes up here. Okay?
I just want to follow that bit, when you said, but ax plus b such that x belongs to R. What do you mean?
Wouldn't it, even if it was just the b, it would still be a real number?
A and B are fixed, though. Like we've chosen like a particular t.
So
A and B
yeah.
are fixed, so x can be any real number though, because you're looking at the whole
Oh,
queue.
right, yeah.
This is the
Yeah.
point, yeah.
Yeah.
So like, remember, x could be anything here. And indeed, U consists of every matrix here where you've got any x here. So you've got the full infinite collection of matrices. In the coset, you're getting matrices like this popping out. Now, x is varying across any real number. So that in effect means you're looking at the collection of these matrices, where the top right entry varies across any real number. Okay? Because if you want ax plus b to equal some number y, if you want y, can you make ax plus b equal to y? By choosing an x? Well, the answer is yes, because this surely has a solution. It's y minus b over a. And that's only valid, of course, if a is non-zero, but a is non-zero. So we can obtain any real number here just by choosing a suitable x, xv y minus b over a. And x is unrestricted. Yeah. So now he's got insight, and now we have insight into what a typical left coset looks like. It consists of every matrix which looks like the representative in these three entries, and we don't really care what's in the top right, because you can have anything at all. Okay. So now he argues for this equation here. Okay. Except he calls them T and T prime rather than T1 and T2. T and T prime. So here's a generic pair of matrices from capital T. The key point here is you examine the product in either way to get this representative. The key observation point is that these three entries here are the same in each case. AA prime, 0, CC prime. AA prime, 0, CC prime. Even though we've multiplied them together in the opposite way. Now, the top right entries come out as different, but we don't care. Because when you pass to looking at the cosets, the top right entry is of no interest because it goes through every possible value. So now with this observation here, the left coset for TT prime consists of all matrices like this. The left coset for, and that has to be the same as the left coset for T prime T, because T prime T has these exact same three entries here. Okay. So that establishes this equation here. So this equation is no longer a question mark. This is true. So this one is true. Okay. Therefore, the product of cosets this way around is equal to the product of cosets that way around. So the group is immutable. Factor group is immutable.
So you say that one is equal to which one?
So his observation here is that this left coset is equal to this left coset. They're, from the beginning, if you just walked in the door, you might think they might be different because they've got different representatives. But because of this work, right, we've already identified that really the crucial thing about the left coset is just what these three entries are in the matrix. The A to Z, these three positions. The point is, these two products, which are different matrices, but the point is in these three positions, they're the same. AA prime, AA prime, CC prime, CC prime, 0, 0. These are different, but we don't mind.
Is that the second matrix ABC? Are they crossed?
They're crossed out. They're corrected. So the first one is TT prime. So ABC, which is T, and T prime, which is A prime, B prime.
Okay, and then if you do it like that.
The other way around here, so these are he's corrected himself here. This is just unadorned A, unadorned B, unadorned C.
Okay.
A nice word, isn't it? Unadorned.
That's a good one.
So this is this product. This and these top right entries are different, but the other three are the same. It's key observation. Scared them off. Okay, so that establishes that the factor group is B. Final part. Is T normal in the general linear group, prove or disprove? Okay, so this is a harder type of question. It's an investigation type question. I haven't given you a definite conclusion to get to, so it's either going to be normal or not. Notice he's still making use of this same principle that we made use of before. When you conjugate the subgroup, do you always end up back inside the same subgroup? So if you zero into the crucial equation here he's showing that he's found a conjugate. He's found some particular matrix G that when you conjugate a little t by G, so a particular little t by G, you end up outside of T. So you can see here, what he's found is a counterexample to this condition. He's found a counterexample to this condition, which will prove that U is not normal within the general linear group. So with a bit of experimenting around, a bit of side calculations, thinking about it, he's realized it's going to be non-normal. So I think what he's done is he's just chosen the simplest possible matrix he can think of that lies outside of T. So that's one of these new elements that's going to break the normality of U. Remember, U is normal in T, we know that. So we're expanding out the containing subgroup now to the whole of GL2R. For constructing his counterexample, he has to choose a representative outside of T. If you choose a representative in T, he's just going to observe normal behavior. Left coset equals right coset. He must take a representative from outside of T, but within GL2R. I think what he's gone for is, you could argue this is the simplest type of matrix you can write down, which is not in T. So this is the point here. You could augment his thing here by saying this is in GL2R less T. So it's outside of T. It's one of these new elements we brought in.
Because it's got one.
There. Yeah. So it has a non-zero the bottom left entry. Therefore, it's not in T.
Non-zero. But why did you make that entry 0?
Because that's the simplest possible choice for this entry. Just to make his life easy.
Do we
Indeed.
have to make it 0 or no? We can just leave
No,
it one?
it could be anything. 57.
It
Anything.
could be 1.
It could be anything. But in order to make the calculations easier, choose it as 0. Okay?
Mm-hmm.
So this is certainly in GL2R because it's got determinant 1. So it's a non-singular matrix. He's going to do conjugation with this, so he works out its inverse. Inverse is nice and simple as well. 1, 0, 1, minus 1. And what's he doing here? So here he's just working out the conjugate. Yeah, okay. What was he doing here? No. So he wants to show that what he wants to construct a counterexample to show non-normality. So he wants to choose a particular T that's going to evidence this non-normality. So he does a quick investigation. He takes a typical element from capital T, and this is the conjugate of it by little g. So he's working out little g, t, g inverse here. The little g, t, and that's this product, and then he times it by g inverse on the right. So you get this matrix. So then what he asked himself was, is this matrix in T, question mark? Now, he wants to choose, what he wants to be sure is that he wants to choose parameters A, B, and C. He wants to choose his little t to be sure that this ends up outside of T, because he wants to evidence the breaking of normality. So this guides him here. So to evidence that you're not in T, you have to end up with either you have to end up with something non-zero here. So his guidance was just a quick and easy choice of A, B, and C to end up with something non-zero here. So choose A, B, C equal to all 1. A, B, C are all 1, then you got minus 1 there, so you're okay. So he lays that all out then. This is his concrete choice of little t. This is our little g. Conjugate t by g, you get this. This is not in T because of this entry here, isn't it? So because of this example, we know that this subset inclusion is broken. Yeah. So therefore T is not normal in GL2R. That is admittedly, that is the harder type of question, because if you don't know if it is or it isn't normal, then you got to do some investigation. In fact, you got to embark on trying to prove it is normal, perhaps. If you succeed in the proof, fine. If the proof grinds to a halt, doesn't look like it's going to be possible, then you suspect it's not normal, then you search for counterexample to evidence exactly that the proof is going to be impossible. Yeah.
Why did you choose G as that?
So this G was chosen as kind of the simplest possible matrix that was not in T,
Not in T.
I think.
T, that is like A, B, 0, C.
Yeah.
Okay, yeah.
So he just makes this non-zero. And he's allowed to have this as anything. And but these two have to be non-zero. Because remember, A times C has to be non-zero. So 1 and 1 are the simplest. Yeah. So the answer to that question is not always. See, there would be some poor choices of little t. If you chose little t with A and B 1 and C 0, then you wouldn't find the counterexample. Because you we can't have C 0.
If you
Okay.
had A equals 2 with B and C equal to 1. then you didn't
Yeah.
need to.
So there are some bad choices of little t. But actually, probably most of the time is probably the answer to that question.
But just not C. Not C.
B equals 0, A and C, B,
Yeah.
both being 1s.
Yeah, the identical.
Yeah. Okay, we better finish this 5 to 3. So finish there. I'm going to see you tomorrow. We'll force on into questions 5 and 6. Discuss questions 5 and 6 tomorrow.
Thank you so much.